Hey guys, welcome. All right. Hey, listen, I'm admitting some of you that are showing up as guests for some reason. I have to tell you that up until today, it was the case that once the meeting got started, I could click a button and all guests would be admitted automatically. They seem to have taken that liberty away from me now. So I'm going to try to watch to make sure that no guests show up late, but if for whatever reason you do have to come in late, it's really to your advantage to sign in through whatever the UT mechanism is. Let's see, who is this here? Wu Yu, Xia, you have a question or comment?
Yeah. Hey, sorry. Professor, do you know what the university is doing about Easter this year, if they're doing anything at all?
I'm not exactly sure what the question means because we don't ever do anything about Easter. So this is a period of the Christian and Jewish religious calendars, but the university maintains a master list of all the religious holidays for basically every religion on the planet, just so that when students come to us with religious observance or something that's going to restrict their schedule, then we know about it in advance, and we are advised not to hold exams and things on those days, at least for the most numerous religions on campus. But today is a school day, and Monday is a school day too. So I guess some of you, because it's a Good Friday observance, you would be absent right now. I'm obviously speaking to people who are not here. Do you want to flesh out your question a little more? What did you want me to say about Easter as far as UT goes?
Sorry, no, this is just a random thought I had on my mind.
Yeah, no, it's, I mean, there are schools where they just have like when I was a kid, every year about this time, our school was let out for spring break. And just magically, spring break always happened to coincide with the Christian Holy Week. So, okay, fine. That means that we were all home for Good Friday and we would go to church and stuff. But this now, UT is a state-run school, so separation of church and state. We don't officially make any allowances for Christian holidays. Listen, before I forget, because my other class was asking me, I did just mention exams. So let's say something about that. We do have an exam coming up, and I have it scheduled for 2 weeks from today. Oh, Yangzhu, you are asking me a question?
Yes, a question about the theorem that we talked about like last lecture.
The change of variable theorem?
Yes.
Yeah, I will be addressing that for sure. That is exactly what we're going to talk about today. I've had a lot of questions about that, and I'll try to see as many of them as I could clear up. So okay. It's a hard one. I will admit that it's hard. So about the exam, what do you want to do on the exam? The easier thing for me would be to just give you basically a quest exam. It would be like a bunch of quest homework, except it wouldn't be multiple attempts. But I've had a bunch of students asking me that they say they really want to make sure that they have a free response question so that they can get some partial credit. So the downside to that is if I do that, you guys have to go through some process of writing out your answers by hand and then scanning them. If you don't have a scanner, you can use various apps on your phone. And then you would have to go through Canvas, I guess, to upload it. And then I'm assuming that there's some way for me to, I don't know, write without printing all of your PDFs. I think I can make some kind of annotation on the PDFs. But I don't know, is that we need to find a way to give an exam which is somehow pedagogically sound. In other words, I really need to to probe what you guys know, and I don't want it to be. Hang on, I just unplugged myself here. There. You know, I want to be able to see what you know in a way that doesn't penalize you unnecessarily for making stupid arithmetic mistakes, but on the other hand, it does kind of hold you to the. You need to have the ability to actually compute some things, and I want to see what you understand. So I don't want you to kind of randomly guess the right thing. I also have to somehow prevent cheating. And at the same time, I can't disenfranchise people who are now currently on a different time zone or have, you know, work and family obligations. So it's a mess. It's just a mess. If I tried to just recreate what we had for exam 1, would that work for you guys? Would you be able to scan in your handwritten response to a couple of free response questions? Nobody has a comment. All right, here's what I want to do. If you guys have any ideas for what you do or don't want on the final, for the final or for this upcoming midterm exam, can you drop me a note, send me an email, and I can't, it's just not going to be a great exam no matter what we do, but if I can try to accommodate as many of people's desires as possible, then.
If I could make a suggestion.
Yeah, go ahead.
Would you be able to possibly open up some kind of set of questions for a day or so that is timed? So as soon as you open it, you have maybe an hour or so to complete whatever questions are there, but it's open for the entirety of the day, as well as also putting out 1 or 2 free response questions that are also have to be turned in by some time during the day. Like there's maybe like a few hour time frame in which they're available for us to work on, and then upload them by a certain time.
Yeah, that's actually what I think we're gravitating towards, just that. I mean, rather than me selecting some quest problems and then printing them and then giving you guys a PDF that has those printed questions, I will probably just set it up like it'll feel like a homework. It'll just be set up exactly like a homework, but with a 24-hour window. And that would be 75% or 80% of the midterm exam. And then the other questions, I'll post them somewhere as a little PDF that you can look at on your screen and write out your answer by hand and then scan it back to me. I was just in conversation with the Quest people today, and they said that they do not currently have a format for inputting scanned answers, but Quest does, so we'll have to do it that way. Is that
okay? Yeah, no, because I think by doing it that way, not only we get both the free response and the multiple choice questions, and it also kind of works around the whole difference in time zones and issues with Wi-Fi and uploading and stuff like that.
Yeah, the only things that are wrong with doing exactly that are, number one, I'm not exactly sure how I'm going to be working it on my end to grade these things. I mean, I can stare at the screen and look at your answer and give you a number, but I know you want feedback, and I'm not sure how well I'm going to be able to move my mouse and write a little comment and that kind of thing.
When in doubt, you can just turn it into an image and put like little text boxes everywhere.
Yes, although it's not always text that I want to give you. I want to show you how your integral needs to be changed or something. I mean, we'll just have to do our best. Just like this whole semester, we just have to do our best. And the other issue, of course, is cheating. I don't know what to do. I'm going to have to trust you guys. The university is proposing all kinds of crap where I observe you like Big Brother or whatever.
One of my professors is having us, we're still having a free response test, but one of the pages that we have to also upload is basically just a sheet that has our name and an honor statement and us and our signature at the bottom as a kind of reinforcement to abide by those rules. I don't know how well that would enforce anything, but it would at least.
Well, I'll tell you, when I was in college, the instructors were forbidden from being present while we were taking exams. That was not only the default, it was like the forced default. They would give us the exams and then leave. And we could leave, we could go to our rooms. It was completely on the honor system. And so I had, every time I turned in one of those papers, I had to say, I pledge my honor that during this exam I have neither given nor received assistance. Except in my German class, I had to write it in German. But see, the thing was that there was a well-established, the honor code had been around for, well, centuries, literally. And there was a student group that actually policed it. And anytime that there was an allegation of cheating, it went before the student panel. And I got to tell you, the students were harsher on their fellow students than the faculty were. So yeah, occasionally somebody would be thrown out for cheating. But we don't, I mean, I know that you guys have an expectation of honesty. You guys are all good people, I work with you. But there isn't an institutional setup. I mean, yes, there are students that cheat, and I've gone through the whole process of reporting them and stuff, but let's just not do that, okay? Can you guys just promise that when I give you an exam question, you will follow whatever rules I set down? For the homeworks, when you do the quest homeworks, of course you can use whatever resources you want. You can work together. I want you to learn in the homeworks. And you're doing it, so that's great. And now the exam will be a similar setting, but I'm going to ask you not to consult with any human being. We'll have to decide what kind of, I guess it'll be open book too, but anyway, we'll have to see exactly what the rules will be, and I'll have to trust you to follow them, okay? So be nice. All right, let's get busy. We've already spent 11 minutes talking about this, and it's important stuff, but the other important stuff is to do some math. So I got some, we're going to talk about that change of variable theorem. It's important, it's difficult, and I'm going to get you started by having you do a problem. I want you to spend a minute or two on this Calc 2 problem. So grab a piece of paper and a pen, because I know some of you are just staring at a screen. And tell me how you're going to evaluate that. I'll give you some Jeopardy music while you work. Do, 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 do. All right, somebody tell me how you would begin to address this kind of an interval. Well, let me pause for a second. So you know that I've given you a very particular function here. You could graph it in the xy plane. You only need to graph it from x equals 0 to 2. You draw the graph. I'm asking you for the area of the region that's under that curve and over that interval. So it's some number. I actually don't know what the number is. I don't care. But I do want to know how you approach the problem. So somebody tell me, how would you begin? I'll give you a hint. I can think of 2 different ways that you could address this. How would you begin to evaluate this integral? Come. I know you all did something.
Trig substitution.
Trig substitution. So specifically, what should I write down after the word let? X?
X equals to 2 times t.
2 times the tangent of t? Okay, t. All right, and then you're off and running because you guys know what you're supposed to do here. You have to use this expression for x to rewrite the integrand. You'll also have to rewrite the differential, which will require differentiating this thing. And then you'll get your new limits of integration on x. And in fact, I've already written out all those steps for you so that you can see how that would go. I didn't use the variable t, I called mine theta. But these are the steps that you would have to go through. How's that? See that a little better? So you told me to have x be expressed in terms of a tangent of a new variable. Of course, algebraically, you could rewrite that the other way around. You could introduce the new variable as a function of x. These 2 formulas are equivalent. But you don't need this right away because all you're going to do is differentiate this expression to get what dx over d theta is, or you multiply through by d theta is to get dx expressed in terms of d theta. And you use this top line to rewrite the integrand. There's a little trig substitution, a trig identity involved. 4 plus this thing squared would be exactly 4 times the secant squared of theta, so there's your square root. And then the differential, the dx, gets replaced by all of this junk, so there's a couple more secants involved in there. Now, your Calc 2 teacher might have encouraged you to do all of this. You get a function of theta. You anti-differentiate that function of theta to get a new function of theta, and then you substitute this thing in to get everything expressed in terms of x's. Once you do that, you can plug in these two values for x and get your number. I don't do that. I encourage my calc students to say, look, if you're going to rewrite the integrand and rewrite the differential, you might as well rewrite the limits of integration too. Get rid of the x's once and for all, express everything in terms of theta, and then your integral will be an integral over this range of thetas. You go from theta to pi over 4. And now you do exactly what you think you need to do. You find this antiderivative. It's actually a bit of work to get the antiderivative of secant cubed, but you can do it, and then you plug in these two endpoints and you get some number. Cool? So I suspect that a lot of you knew to do that because you guys all graduated from Calc 2. But I can tell you from having taught Calc 2 that a lot of people have another substitution in mind. Would anybody else want to try another substitution? Anything else that you think you could try? No? Nobody did anything different? All right. Well, you could have. I mean, a perfectly natural thing to try at this moment would have been to say, look, I've got the square root of something complicated. Let me just call that complicated thing u. Once you've decided on what u is, you differentiate that to get du in terms of dx. So you'll be able to get rid of the dx that's over here by, well, first you have to divide through by the dx to get the dx, excuse me, divide by the 2x to get the dx isolated. And now that'll be something that you can substitute in, but remember the goal is to get rid of all of the x's, including that new x that showed up. But you can do that because from this first line, you can invert this formula to say what x is in terms of u. And that would give you something that you can write in for the differential, so that now dx is expressed only in terms of u's and du's. And now you rewrite the integrands to involve only the new variable. There's the original integrand has been rewritten in terms of u, and the differential has been rewritten in terms of u. And I've even done, like I said on the other side, I've changed the limits of integration so that they are expressed in terms of u. So, as it turns out, as in the case over here, what you end up with is a new integral, which looks actually pretty miserable, but you have some hope maybe that you could evaluate this integral. I mean, you've got a graph, a function between u equals 4 and u equals 8, and so there's a range of u's that you have to deal with, and for every one of the u's, you're trying to find out the area of the region that's above the horizontal axis and below the curve of this function of u. I won't do the numbers, but we could. All right, so what you should see in common with these two approaches is, in both cases, you've chosen a new variable that you're going to use instead of x, whether it be u or theta. You've got a new variable in mind, and you will get a new integration problem to do that will involve that new variable. You see the new differential show up. You see some expressions that involve the new variable, and you see a range of values of that new variable. There's a little bit of a difference, though, between these two approaches. In this case, what you did was you told me how to write the existing variable x in terms of the new variable. In this case, we did it the other way around. We introduced a new variable and told how to express that new one in terms of the original one. So these two are kind of opposite ways of introducing a new variable. In each case, we can, and in fact, I had to in one case, in each case, we can take the algebraic formula that we came up with after the word let, and we do some algebra to solve it to write it the other way. So both of these approaches now express x as a function of the new variable, and both of these approaches both express the new variable in terms of x. It's just that when you went for this particular substitution, it felt more natural to begin with this kind of a formula that expresses x in terms of u, whereas in this case, it felt more natural to express u in terms of x. Well, naturality is not really a mathematical concept. That's a human concept. Mathematically speaking, these are both doing exactly the same thing. You're expressing the existing variable in terms of a new one, or expressing the new one in terms of the existing variable. And then as you go to do your calculations, you notice that, well, whether it was more natural or not, that's a human thing. And whether it's simpler or not, that might also be a human thing. Look, in this case, it was easier to get dx directly in terms of the new variable. Give me something to substitute into here by doing one differentiation. In this case, I had to go through a couple of additional steps to get something that I could substitute for the dx. When it came time to getting the new limits of integration, this was the one that was simpler, because now I just take those two values of x and shove them into this formula to get the values of u. In this case, you have to think a little harder and say, well, if I want my x's to go from 0 to 2, then that'll mean that the tangent of theta will have to go from 0 to 1, and that will mean that theta itself should go from, say, 0 to pi over 4. So doing it with an x equals approach maybe made it a little bit easier at this stage. Using it in the u equals approach made it a little bit easier for this part. But they're both valid, okay? In both cases, you've got a new integral expressed in terms of the new variable, and it's integrated over a portion of the real number line that's indicated with that new variable as its coordinate. Whether it be u or theta, we have a new interval to play with. In both cases, that new interval is kind of naturally related to the original variable, the new interval of x's. You have functions that go back and forth between the x real number line and the theta real number line. The two functions undo each other. They're inverses of each other. One tells me how to get x in terms of the new variable. That's here, these two formulas. And the other goes from the x real number line to the new copy of the real number line by expressing the new variable as a function of x. So you've got a pair of formulas here that are inverses of each other. You've got a pair of formulas here that are inverses of each other. Maybe this one felt a little more natural and that one felt a little more natural. But you have them in both directions. These functions that go from the new variable copy of the real number line into the existing one, this is the function that I've been calling capital T. And this other one, I'm going to call this W. So they're a pair of functions that are inverses of each other. Each one of these pairs of functions goes from the real number line to the real number line and back. And in both cases, capital T is the one that goes from the new variable system to the original variable system. All right, with that in mind, let me show you the statement of the change of variable theorem. That's this theorem right here. We have just done, in this example, we have just done the one-dimensional version of this. So take this n to be the number 1 in here. And I'll read this, what that says in this case. Suppose that d1 and d2 are subsets of the real number line. d1 and d2 are just intervals. And suppose that t is a function that carries one of those intervals to the other one. It's supposed to be almost anyway, a one-to-one and onto function. There's the word bijection. I won't go into the technicalities, but I guess you guys kind of know what I mean. I want these two intervals to correspond to each other in exactly the natural way that you saw in those examples. Now, if you have a function that you were supposed to integrate over this interval, then the change of variable theorem guarantees that you will get the same value if you were to integrate a different function over a different interval, this other interval here. If you choose to change the interval, you may do so, but you're going to have to change the integrand to match. Specifically, you do it but in two stages. You rewrite the original integrand in terms of the new variables. That just means you substitute in the formula that says, how did you get x from the new variable? Substitute that in so that you no longer have a function of x, you have a function of this new variable. And then in addition, you need to multiply by something that involves the determinant, not the determinant of the function you're integrating, but the determinant of that transformation function. That's exactly what, oops, where did it go? That's exactly what this factor is over here. This is the derivative of this transformation function, the one that says how to get x in terms of the new variable. If you differentiate that, you get the extra fudge factor that shows up. This other part of the formula simply comes from substituting in your formula for x in terms of the new variable. You substitute that into the function of x that you had in the first place. And then you just have to integrate over the interval, the range of values of that new variable that sort of corresponds to the range of variables that you had for x in the first place. But the theorem is phrased in terms of a function that maps into the x range. I have to express things in terms of this function, capital T, that maps into here. I can use exactly the statement of the theorem to calculate this integral in terms of u, but I have to use this statement, the theorem as it's stated, I have to use the function capital T that expresses x as a function of u. This one maybe feels easier to work with. This felt more natural in this particular setting. But you notice that, yeah, sure, that was natural. Its derivative was easy to compute, but I don't end up multiplying by that derivative. If anything, I end up dividing by it. You see, it's in here in the denominator. And I could express this all in terms of that inverse function, but it turns out to be kind of screwy because you'd have a division instead of a multiplication, and here it's not even quite clear what you would be doing. But if I decide to express this change of variable procedure, not using this formula, but by using this other formula that says the same thing in a notation that feels a little more complicated, well, if I just go step by step through the rules of what this theorem says, then you will see that you will get exactly what I had written down earlier. This part will be what you get by taking the original function and replacing every x by this formula that involves x. So that's the f composed with t part. And this other thing that has something in the denominator, that is exactly what you would get if you took the derivative of this function of u. If you take its derivative, you'll get 1/2 times this quantity to the minus 1/2 power. That's why it's in the denominator. It's a negative 1/2 power. Okay, so this is the statement of the change of variable theorem, and you have just seen it in play in the one-dimensional setting. It matches exactly what you did in Calc 2 when you had substitutions, but to make it match what we did here, you have to realize that the change of variable formula requires having the function that expresses the original variables in terms of the new variables. You need to talk about the function capital T that goes into the original coordinate system. The same is true when we started to do our problems in polar coordinates. So I don't need all this stuff now. So our other example used polar coordinates, and I'll remind you of the example that we did there. We had some sort of a function to integrate. I don't remember what it was. I really don't care. But I had to integrate that over a portion of the xy plane. I don't remember exactly what it was. I'm pretty sure it was a quarter of a disk. Maybe the disk was of radius 3. I can't remember. But anyway, if you want to express this thing in Cartesian coordinates, you know how to do that. Fubini's theorem says exactly what you're supposed to do. You write this as a double integral of exactly that function. There's the function you're integrating. The little area element, I should have written a dA there. In Cartesian coordinates, that's just expressed as a product of the dx and the dy. And as far as the limits of integration, we've talked about how to do this. You have to scan this whole set, asking for the minimum and maximum values of the y coordinate, which I guess would be 0 and 3. And then you would hold the y coordinate fixed, and you would ask for the minimum and maximum values of the x coordinate. The x coordinates go as low as 0 on the left, and on the right, the x coordinate would be, I guess, the square root of 9 minus y squared. So this turns out to be a very easy integral to compute in Cartesian coordinates. There's nothing wrong with that. But I want to have you see that we could do the calculation in polar coordinates by using exactly what it says to do in the change of variable theorem. The change of variable theorem says that if you want to integrate that function, oh, I'm sorry, I should be pointing over here. Hang on. Right, if you want to be integrating that function f over that region, that's going to be the D2 over here. You can do that using polar coordinates. It's going to be re-expressed as an integral of a different function over a different region. This new function will come by multiplying together two parts. The first is just exactly what you would get from the original integrand, the 3x times y squared. You're supposed to take the composition of that function with this transformation that we use for polar coordinates, and I haven't written it down yet, so let me remind you what that is. So I'm going to use the function capital T that goes from the plane to the plane, and it's defined by T takes a pair of numbers, which I call r and theta, and it spits out a pair of numbers, which I call x and y, and it uses the following formulas to compute them. Take those two numbers and first compute this, then you compute that. If I ask you to compose this function with this function, that means you're using the outputs from this function to become the inputs to this function. The outputs are going to be the x and the y that I plug in here. So the first part of my integrand is just a substitution. I'm going to take 3 times the x coordinate times the y coordinate. Oops. Sorry, the y coordinate squared. Now, there is another piece of the formula in the change of variable theorem. I've called it a fudge factor before, and I've indicated that this has something to do with how areas get changed by the transformations. But let's just see the formulas in action. If I look at this function and compute its derivative, we did this last time. Remember, there was a pair of gradients of those two functions of two variables. We got these formulas, minus sine of theta, and r times the cosine of theta. And I found that when I took the absolute value of the determinant of the derivative of capital T, that just came out to be an r. So, according to what the change of variable theorem says, I have now got two of the portions of this that I need to deal with. There's two parts of the original integrand that have to be dealt with. There's the integrand itself, and there's the differential. And now I've written those two parts as being, the one of them is 3 times, I guess it's r cubed times cosine of theta times sine squared of theta. And the other part is going to be r times the area element that I use in the r theta plane. I can write that as dr d theta. All right, so the two things that I've underlined have turned into this portion of the new integral and this portion of the new integral. They are exactly analogous to what I had in the Calc 1 setting, where changing this integral gave me this portion of the new integral and this portion of the new integral. The third thing that I had to change was the limits of integration. The region over which I'm integrating is no longer going to be the interval from 0 to 2, but that interval. And in our setting, I have to know what is the region in the r theta plane that I'm integrating over. That's kind of hard. But in this case, it's really not too difficult to figure out. And I'm going to propose a mechanism that I want you guys to think of. I actually worked this out with you last time. When we got these limits of integration, the way we did that was to wander around the whole region that we started with and ask about the x and y coordinates of these points. We wrote down the minimum and maximum values that we got for x and y. In the one case, we were holding y constant when we let x vary. To get my new limits of integration, what I want to do is exactly the same procedure, but wandering over that same set in the xy plane, I can figure out what are the combinations of r's and thetas that we're mapping onto it. The capital T that's going to map onto this quarter of a disk in the xy plane, oops, that was supposed to be a straight axis, sorry, will be some combination of some set of combinations of r's and thetas in the r theta plane. And to figure out what they look like, I simply wander over this region, and instead of asking each point for its x and y coordinates, I ask them for its r and theta coordinates. Specifically, I've written this thing down with theta on the outside, and so I need to talk to all of these points about their r and theta coordinates. Now, to help you visualize those, I'm going to recommend that you put in the picture of the level sets for the coordinate functions. The kinds of curves that you get when theta is held constant or where r is held constant. Because if I say, please tell me about the range of values that you get for theta, tell me the minimum and maximum theta coordinates that you need, you know that you need to be staring at these different rays one at a time and figuring out which ones actually intersect our region. The one that has the smallest theta coordinate would be this ray. That corresponds to having theta equal to 0. That's the smallest theta coordinate that I would ever get when I talk to these points. If I go in the other direction, the counterclockwise direction, I'll get my maximum theta coordinate, and that shows up for all of these points. They all have a theta coordinate equal to pi over 2. To get my next limits of integration, I need to hold the theta coordinate fixed and ask the points that have that theta coordinate about their r coordinates. So let me take, within my quarter disk here, let me just look at the set of points there that have a fixed theta coordinate, and that would be this line segment. And now I need to talk to these points about their r coordinates. As you know, the minimal r coordinate occurs when you go as close to the origin as you can. The biggest r coordinate is when you go as far away from the origin as you can. So I'll write down the r coordinates that I get for this point and that point, because those will be the minimal and maximal ones. This one has an r coordinate of 0, and if that was a quarter disk with a radius of 3, then the maximal r coordinate is a 3. As far as doing the integration calculations, you may sort of stop at this point and start doing some arithmetic. I mean, you have to anti-differentiate with respect to r, plug in some endpoints, anti-differentiate with respect to theta, plug in the endpoints, you'll get your numbers. But let me also point out that you can visualize something that I think will be helpful. You are here describing all of the combinations of theta and r that show up when you talk to the points in your quarter disk about their r and theta coordinates. When I talk to every point about its r and theta coordinates, what I find is that their theta coordinates are between 0 and pi over 2. In other words, I get their x and y coordinates from that formula, this formula. I'll use this formula with some value of theta that is always going to be between 0, here's where theta equals 0, and pi over 2. And for each fixed value of theta, if you think about the r coordinates that you need to get all the points that were on that line segment, you need all the r's that are between 0 and 3, and that's the same answer of what r's are necessary no matter which theta you were looking at. So for all of these horizontal lines, the range of r's that you need always varies from r equals 0 to r equals 3. That's true whether you're on that horizontal line or this line where theta is a different constant, or here where theta is a different constant. So those are your ranges of r's that you have for each theta, and I've already told you your range of thetas. So the combinations of r's and thetas that you have in the r theta plane completely occupies this rectangle. So in the statement of the change of variable theorem, this rectangle here is the set D1, and this quarter disk is the set D2. And I used the transformation that took each of these combinations of r's and thetas to create a combination of x's and y's. That transformation takes the combinations of r's and thetas in the rectangle and produces a combination of x and y's, which is inside the disk. I tried to illustrate this last time with my little paper fan. If you squeeze this, then that uses the fact that all the points with r equal to 0 come down to the same spot in the xy plane. So if you like that little image, you can see something kind of kinematic, but if you don't have that, don't worry about it. Just understand that this is illustrating the change of variable theorem carrying one region in one copy of the plane to a different region in a different copy of the plane. All right, a hand has gone up here. Let me, Yang Zhu, why don't you ask your question?
Yes, thanks for your clarification, but I have one question, is that why we use the determinant rather than the derivative of the matrix?
Well, I don't know what to do with a matrix. I mean, if I was to start writing down an integral like this, what am I going to do if this number r gets instead replaced with, where'd that matrix go? Here, this matrix. What are you going to do if you put that matrix into there? I don't know how to put a matrix into an integration formula. Now, a better question is, well, why is, okay, so capital T prime by itself doesn't seem to be useful, but how do I know that the determinant of T prime is useful? And I think I mentioned last time that actually is a question that you should ask a linear algebra teacher, because when you stand near a particular point in the set D1, capital T is going to transform all the points around you into a region in the XY plane. Approximately speaking, it's going to take points near where you are and transform them according to this 2x2 matrix of numbers. You take your theta and r coordinates and stick them in here, and you'll get some numbers. That'll give you a 2x2 matrix of numbers, which is a linear transformation that will take your little neighborhood here and approximately show where your image neighborhood would be in this case. And here's the thing from the linear algebra course, is that for a linear map, linear maps do change areas, and the amount by which they change the area is exactly expressed by the determinant. So since this isn't a linear algebra course, I won't try to explain why that's the right theorem. It's actually easiest to see once you get to things like eigenvalues and stuff. But we'll just take that for granted in our course, that the determinant somehow measures it's the fudge factor that says how much areas get transformed.
Okay, another question is that if we define determinant like that, or given the property of determinant, why we use the matrix, the derivative of the matrix, rather than the original matrix, like the matrix that transformed the...
No, but that's not a matrix. I mean, you could say it's a 1x2 matrix, but in order to compute a determinant, you need a square matrix. Basically, the problem is that this is not a linear function. I need to have a linear function, at least in the vicinity of any one point, because linear functions, I know that the determinant of a linear function is the thing that measures how areas change. So taking the derivative would give me at each point, this becomes a linear function. So it's a 2x2 matrix.
Is that saying that we first approximate a nonlinear function into a linear function, and then we use a determinant? Yes,
that's exactly what we're doing. You may remember that from early in the semester. That's part of how I introduced what the point of a determinant, how a derivative was, is the derivative is the thing that gives us the best linear approximation to a function like capital T near a particular point in its domain. This is the domain of capital T. Capital T is defined at these points in the r theta plane. So near any one point, that's why I drew a little neighborhood to stay near there. Near this point, you could approximate what capital T is doing by using this matrix. I'm a little loath to actually do a numerical calculation to illustrate that because we're kind of running short on time, but I could if you want to come by in office hours.
Okay, thanks.
Now, there's two things that I want to do with this. I want to show you a further example of doing the conversions with polar coordinates, and I also want to show you a non-polar example. But what I wanted to get out of this example is, because we kind of did this one last time, but what I didn't do well enough, I don't think, last time, was to emphasize that the formula that expresses x and y coordinates in terms of r and theta coordinates can be thought of geometrically as a function that's mapping from the newly created coordinate plane into the existing coordinate plane. You're getting your x and y coordinates from your r and theta coordinates. So you're turning points over here into points over there. That matches this notion of what it means to do a substitution in Calc 1, but it's opposite of this notion of what substitution meant. So several of you were asking because you kind of wanted it to look like this part, and it didn't feel like it was looking like that. Well, instead, it's looking more like this, although you could have written this one so that it did look like this. That's, I guess, the point that I'm trying to make with this one example. Now, let me show you. I said I wanted to do a second example with polar coordinates, so let me run through that one. I think we have enough time to finish that one. Suppose that I ask you to integrate that same exact function, but not over a quarter of a disk. Maybe I would want to integrate it over a little triangle. And specifically, I mean to look at the triangle that's between the x-axis, where y is 0, the y-axis, which is where x is 0, and let's have a line in here like the set of points where x plus y is equal to 2. Any normal person would calculate this thing in Cartesian coordinates because the function itself is already expressed perfectly fine in Cartesian coordinates. The area element can be expressed in Cartesian coordinates as well. And the limits of integration are easy to get in Cartesian coordinates. Let's see, I need y to go from 0 up to, hey, what do I put as my upper limit of integration on y? I need the maximum y coordinate that you see anywhere in this set. What's that?
2.
2. How'd you get 2?
Y is at a maximum when 0 is at its minimum.
Yes. You didn't say what I wanted you to say. You got it because the maximum y coordinate is the y coordinate of the northernmost point. I can see it. How do I describe it? That northernmost point is the intersection of this line and that line. Oh, so its coordinates have to satisfy those 2 equations. 2 equations and 2 unknowns. You can solve for the unknowns and in particular get the y coordinate. Okay? Keep that thought in mind because that's how I'm going to get my limits of integration in polar coordinates too. Anyway, once the y coordinate is known, then you get your x coordinates by going as far to the left and as far to the right as you can. You ask each of these points about their x coordinate. You can already see this guy has an x coordinate of 0. And well, this point with the maximal x coordinate, it's on the intersection of those 2 lines. So you have to pair off these 2 equations. And from those 2 equations, you know that the x coordinate will be 2 minus y. All right, easy to do in Cartesian coordinates. Nothing wrong with it. I know you guys could finish that and get a number. But you can do it in polar coordinates as well. You might not have any reason to want to do it, but I want to illustrate how you could. And especially that would be useful if I have a different integrand that somehow sounded more like polar coordinates. Here's how I would do it. According to the change of variable theorem, you have to change 3 things. Rewrite your integrand in terms of polar coordinates. So we already did that in the previous problem. That much has not changed. Next, rewrite your differential in terms of polar coordinates. And if you just stick with polar coordinates all the time, you've got that one already memorized. You know that that just turns into an extra factor of an r times dr d theta. And the third now is we have to change our region of integration. So I had 2 choices. I could have put d theta and dr. I chose to put dr and then d theta. So I guess now I'm stuck. I have to put the limits of integration on theta first. So now you need to wander over this set asking all the points for their r and theta coordinates. As in the previous example, you want first the minimal theta coordinate, which means the clockwise most points, which are these points, and you know they have a theta equal to 0. To get the maximum theta, you want the counterclockwise most points. That's the theta coordinates of all of these points. It's a multi-way tie. They all have theta equal to pi over 2. Now, you want to draw this kind of a figure again. Scan your whole set and stay along this line where the theta coordinate has been held constant. So you have just this much of the triangle left, just one line segment. You talk to these points about their r coordinates. Obviously, the minimal r coordinate is that guy's, and the maximal y coordinate is this one. So you've got r equals 0 on the inside edge, and on the outside edge, you need the r coordinate of this point. How do you get it? Well, as always, describe that for me. It's a point that it's on this line, on this ray, so it has a fixed theta coordinate, and it's on that line, so it satisfies the equation of that line, which unfortunately was expressed in Cartesian coordinates, but I can re-express it in polar coordinates. So now I have two equations in the two unknown polar coordinates that would let me get the polar coordinates of this point. And the one that I really care about is the r coordinate, and you can see that just from this line here. It'll be 2 over cosine of theta plus sine of theta. So now you've transformed your integral. You did all three parts of the changes: the integrand, the differential, and the limits of integration. But as in the previous example, I want to draw a picture for you. You're trying to get this triangle expressed as the output from this function capital T. And your question now is, well, what the heck was the region, the thing that I call D1 in the statement of the theorem, what's the region of the r theta plane that gets mapped onto this? Well, as before, we have theta coordinates that go as low as 0 and as high as pi over 2. So those are two lines that go perpendicular to the theta axis. And now if you hold theta fixed at some value between 0 and pi over 2, you have a range of values of r. No matter which horizontal line you draw, you're always going to have your minimal r coordinate be 0. But your maximal r coordinate is going to be this funny function of theta. And I know it feels hard for you to graph, but I happen to know what that one looks like. It's actually got a couple of vertical asymptotes down at theta equals negative pi over 4 and up at theta equals 3 pi over 4. But with just within our range of thetas, this top edge would be, it's the set of points where the r coordinate, that's the horizontal coordinate, is calculated from the theta coordinate, the vertical coordinate, by this function of theta. If you plug that function into your calculator, it'll give you a graph that looks like this, because the independent variable is horizontal. So this is the region D1 in our case that's being mapped onto D2. You don't actually have to get this picture if you can get those limits of integration, and you can get those by talking to the points. But I do find that, for me, having a picture of this set D1 makes it a little more clear exactly how this fits into the statement of the change of variable theorem. All right, what I didn't do today, I'll have to save this for Monday, is I'd like to do an example with a different change of variable transformation other than polar coordinates all the time. I know you've got some that you have to work on for the homework, so we'll try some of those on Monday. And if we have time on Monday, I'd like to also show you how this works in three-dimensional space. Really, no change. I'm going to quit because we've gone over, but can I leave you guys with a closing thought here? I asked you to think a little bit about any comments that you want to give me about how we should structure the next exam. Can you also take a moment and respond to me about any changes we should make in the format of this course? We've been doing it for 2 weeks now. I guess it's working all right. There's a bunch of you that are here today, but that's not even the half of the class. So one possibility is I could switch to lectures that are all pre-recorded. Then I'd be able to do them a little more carefully and have better slides for you, but then you would lose the possible interaction back and forth. It would mean that everybody would be downloading them at their leisure, look at them when you care to. But I don't want to make a change unless you guys can tell me that that would be better or worse. Or if you have other suggestions for how you'd like the course to be a little different, can you drop me a note? Because we have a whole nother month to go, and I want it to be as pedagogically useful for you guys as it can be. All right. Any final thoughts, last questions or anything? No? All right, then I'll cut us off. Thank you guys for coming. Have a nice weekend, and I'll see you on Monday.